Okay, so for this problem, we're going to prove Lagrange's theorem, and the statement here is that we fix a group G and a subgroup K, and A and B, which appear in part 1, are elements of G, the group. Okay, so first we want to prove that there's a bijection from Ka to Kb. These are right cosets, given by right multiplication by A inverse times B.
Okay. So can we just really pin down how this, what it means to be given by right multiplication?
Yeah.
So you would take an element here. They look like, say, G times A for G and K. And then it would go to GA and then A minus 1B, which is GB. No?
Okay.
Okay, wait, so just let's clarify for a moment. We're looking for bijections from this set, Ka, because a coset is a set,
Yeah.
to this other set, Kb.
Mm-hmm.
And as Ava said, the elements of the set in the domain are elements of the form G times A, where G is in K, and the elements of the form of in Kb are elements of the form G times B, where G again is in K. Okay.
And as we saw with this formula, it literally takes this element to this element.
Yeah.
Okay.
Great.
So, injective or surjective first? Which one do you want to do?
Maybe surjective.
Yeah, sure.
Okay.
I was feeling surjective too.
Because any element GB came from GA.
Yeah, we kind of have a formula for what goes to GB.
Yeah,
right?
Okay.
we know what goes to a given GB, and it's the same G times A.
And since every element here is of this form, then
Yeah.
we sort of have done it.
And since every G gives us an element of Ka, we found the thing that it maps to.
Yep. Okay. Great.
Injective.
Okay, so to show that something's injective, we can show that its kernel is just 0.
Like the identity of the group.
Yeah, I guess.
So are cosets groups? Because we do that for homomorphisms.
Yeah. Oh yeah, is this a homomorphism? I guess there's two things.
It just says bijection.
Oh, so you're thinking that they would have said isomorphism if there was a kernel?
I think so.
Okay.
Or if it was a homomorphism.
Right, yeah, that's what I mean, yeah.
So what's the definition for injective for things that are not rings or group homomorphisms, just for functions in general? Because this is a function in general, not the ones that we usually deal with in this class.
It means that one thing maps to one thing.
Yeah,
Okay.
so if f of x equals f of y, then x equals y is what it means for just functions, right?
So that's what we need to check. So
Okay.
say f of GA. Oh, we didn't give it a name. Let's just call it f.
Okay.
To agree with Eric's notation.
Okay.
F of GA is equal to f of G prime A.
Okay.
And then we need to show,
So why does only the g change?
because the elements here, we've named them where we just changed the G
Okay,
within K.
I see, but okay, right. It's always a because that's k.
It's
A.
always A.
Okay. All right. Good. I'm good.
We need to show that the GA is equal to G prime A with the A.
Yeah.
Okay. No, what?
Well, let's maybe figure out what these are.
No
Right?
point.
So I'm going to erase this because we remember what that means. Okay, so this, I can rewrite that as G A inverse B equals G prime A inverse B. And then using associativity, I can just cancel these. So we see that GB equals G prime B is what this is turning into. Are we okay with that? Is that right?
I'm catching up.
Okay.
Oh, okay. So, right. So I see that we're trying to show that if f of GA equals f of G prime A, that GA equals G prime A, because that's what injective means. But then, what does it mean for f of GA to equal f of G prime A? It
Yeah.
means that G of B equals G prime of B.
That's right.
Okay.
Oh, but this is a group, so everything has an inverse.
Yeah.
Right.
So we can just multiply by the inverse on the
Nice.
right. The inverse of B on the right.
And so
Right.
G is equal to G prime.
Yeah.
And then we multiply by A again, so GA is GA prime because G is G prime.
Oh, so we're going that way, right? Like multiply by B minus 1 on the right, and we get G equals G prime, and then we multiply by A on the right, and so we've gone that way.
Great.
Okay. That's fun.
Yeah.
Alright, should we move on to part 2?
Sure.
Just trying to understand.
Okay, what does a disjoint union mean?
Well, it's like for what was it like? Way back at the start of the class, we had this like equivalence classes, mod n. And we showed that z, like every number was in exactly one of those, and if they overlapped, if they intersected at all, then they were the same set. I think that's what it means.
Mhm.
So it's a union.
Okay.
So every element of G is in one of the cosets, and it's disjoint, meaning that either they have no intersection or they're the same set.
Let's
Oh,
write that down.
and I think we had the word partition. Was that right?
Oh yeah, I forgot about that word. That's a good
Yeah.
word.
So in other words, the distinct K cosets partition G.
Mm-hmm.
Maybe Becca's mini lecture said that too.
I'll have to go back and watch that.
But now we're proving it. Becca
That's
just
right.
said that.
Okay,
All right.
so we gotta show that every element in G is in exactly one coset.
Yeah, I'm going to break this into there exists what? Ka such that G is in Ka.
I guess. Okay. But the thing that's gonna change from one coset to the other is maybe this part.
Yeah, okay, so maybe it is there exists in A. So that G is in the coset that you get from A.
And that would prove that G is a union, but to prove that they're disjoint, well, we can do that later.
Yeah.
First, let's do this.
Okay.
Okay. Well, K is a subgroup, right?
That's right.
And the only thing we know about, well, not the only, but an element that we know is in any subgroup is the identity. So we know that E is in K.
Yeah.
So EG will be in KG.
Oh.
Right?
Yeah,
Sure.
that was easy.
So G is in KG. And so this A that we had to prove existed is G itself.
Oh, I see. So G
Yeah.
is A.
Yeah.
Okay.
That's right.
All right. Thought that was going to be harder. But I guess with a good idea, sometimes it's not too bad.
But like this word distinct is throwing me off. Because like we don't have a coset for every element of the group. Like there's some repeats.
So
Right.
maybe we need to show that if it's in another thing that looks like this times some other element, then as cosets the two things are the same, even if the elements you put here are not.
Is this maybe the disjoint part where like if A is in KG and KA, that KG and KA must be equal as coset? Like they must, all their elements must be the same?
I think so.
Yeah.
But I feel like
Yeah, maybe.
the two words go together sort of, right? Because maybe if it didn't say distinct, then you would think of like doing the union for all G of these things. But since it says distinct, you want to do the union of, only some of them until you cover the whole thing.
Yeah.
Mm-hmm.
Okay, but what I think we showed was that every element is in some coset.
Yeah, so
Yes.
I guess we can write that as like G is equal to the union of G and G of KG.
But as Becca pointed out, not all of them are distinct in
Right.
principle.
Yeah, there's probably a lot of.
So we don't. And once we picked, if we can pick some that are distinct, we need to show that those also cover everything in G.
Yeah, so wait, I think that all we have to do is show that.
So I think the reason what I'm thinking is that if we show that if two cosets are different, or if there's an element in two cosets that those two things are the same, that means that we can throw out like one of those two things because they're the same thing. But what that helps us with is it tells us that if G is in, or if like, yeah, G is in KG, but I had written this as KA instead or something. If I know that KG is equal to KA, I can just get rid of KA, or I can just get rid of KG, but they're the same, so G's in KA. So if I can show that two cosets are either disjoint or the same, that means I can get rid of all of them that are the same.
So
And not lose anything.
maybe assume that you have an element in KG intersect KA. Then we want to show that KG is KA.
Yeah. So I think we want to, like, these are sets. We want to show containment both directions.
Okay.
So we want to show that every element of KG is also an element of KA. So how does X being in both help us do that?
Maybe we can express X as an element like here.
Get rid of this, do you think?
Maybe we should get rid of the top.
Okay.
Yeah.
I kind of feel like I want to use this because this relates different cosets. So I don't want to erase the statement.
Oh yeah, it tells us that they're all the same cardinality, which is something we have to do later.
Oh, that's great. So like if
We've
we can
already
prove
done that
containment, we only need to prove one containment. No, because they're not finite. They're not
These
finite.
aren't finite groups.
If they were finite.
But this part one does finish the cardinality part.
True that.
Right. Yeah. Yeah, because cardinality being the same just means that there's a bijection.
Yeah.
Okay.
Okay, cool.
Okay, so let's take x and kg intersect ka. So I kind of want to unwind this and just say that this means that x is k1g.
Yeah, totally.
It's in that, so it's k some k times
Yeah,
g.
totally.
Yeah.
And x is also some other k probably.
Yeah.
Yes.
Okay, but that means that K1G is equal to K2A.
Uh-huh.
Yep. Right. Yeah.
And K is a subgroup,
Yes.
which means K1 and K2 have inverses in K.
Yes.
So we can say that this means K2 inverse K1G equals K2 inverse K2A equals A.
Nice. Oh, so A is in kg.
Yeah, and this is an element of K. Oops. So this means A is in
kg.
kg. Was that helpful?
So let's see if A is in kg, so A is maybe K3g, then Ka is K3g.
Okay.
But this is just like everything in K times G. And if I multiply everything in K by something in K,
It's still in K.
it's still in K. So this is
It's contained.
contained, that's right.
Alright.
So what did we just show? Did we show that kg was contained? No, we showed K was contained in kg. Great.
Yeah.
But we didn't use anything special about A and G, so
Yeah, if we just multiply by
should-
K1 inverse, then G is
Yeah.
in Ka also. Sorry, what were you saying? I cut you off.
yeah, no, that we didn't use anything special about A and G, so like if we showed that Ka was contained in kg in the same way, but
Find it in place.
switching them,
Yeah.
so what you said.
Okay.
Okay, so going back, we needed to prove the disjoint union thing.
Mm-hmm.
So we've shown that two cosets either don't have an element in common, or if they do, they're the same.
Yeah.
Mm-hmm.
And also, every element is in one coset. So the cosets have to partition the thing, which
Yeah.
is what we wanted, right?
Yeah.
I'm in the middle.
And it means that you can just like throw away the repeats because if one element is in two things, then those two things are exactly the same. So you don't need them to both be counted.
Yeah.
In order to get all of their elements.
Yeah.
Mm-hmm.
Which is where like distinct intersects with disjoint union.
So we had done the union, and now we did the disjoint. part.
Yep.
And then,
Okay.
And the cardinality
That's
comes
right.
from this bijection.
Okay. I think
Air
we're good.
fives?
In Spain, you're supposed to say hi with your elbow.
But Eric and I were talking earlier about how we cough into our
Right, we cover
elbows, so
your-
maybe we should do that.
And he spread it out immediately.
It's okay. If you haven't coughed in your elbow in the past 6 to 12 hours, we're okay.
We're stopping this, right?
Oh, well, we still have a few more parts.
But should it be the same?
Oh, yeah.
Because